Hey guys, Dean Chase here with another geometry lesson for you. Hope everybody's doing great. Let's go ahead and get this thing started with a word of prayer. Dear Heavenly Father, I want to thank you for staying with us, Lord. I want to thank you for all you do. I pray you'll bless my students, guide them, and help them gain understanding from this lesson. We love you, Lord. In Jesus' name we pray, amen. Alright, you guys, so today we're going to be learning how to prove triangles congruent by SAS and HL, which means absolutely nothing to you, but by the end of the lesson it certainly will. This is lesson 4.4, page 240, sorry. So, consider a relationship involving two sides and the angle they form. Their included angle, to picture the relationship, form an angle using two pencils. So here on the screen I have two pencils forming an angle. Anytime you form an angle of the same measure with the pencils, the sides formed by connecting the pencil points will have the same length. In fact, any two triangles formed in this way are congruent, because whatever this angle is, when you open or close this angle will change, but the pencils stay the same length. So if you have four pencils that are all the same length and they form the same angle, it would form two congruent triangles if you were to draw an imaginary line between them. And we'll learn that in postulate 20. The side angle side congruence postulate. If two sides and the included angle of one triangle are congruent to two sides and the included angle of the second triangle, then the two triangles are congruent. So if side RS is congruent to UV and angle R is congruent to angle U and angle RT is congruent to UW, you could say that the two triangles are congruent using the side angle side congruence postulate. Real quick, if they give you, for example, if they were to say, what angle does RS and RT connect to make? RS and RT connect to make angle R. And I just remember that being on some of the homework, so I just wanted to cover that real quick. So if they said, what angle does UV and UW make? Well, they connect at U, so it makes angle U, or angle VUW. Okay, let's keep going. So example 1, given that MP is congruent to NP, which is already marked in the picture, and OP bisects angle MPN, prove that triangle MOP is congruent to NOP. So the first thing we're going to do, like we always do, is we write our givens, okay? MP is congruent to NP because it's given. OP bisects MNP because it is given. Okay. Now we want to look at this and kind of like develop what we know from the given information. Well, we know that if this line right here bisects MPN, what does it do to these angles? It cuts them perfectly in half. So we could say that angle MPO is congruent to angle NPO because it's an angle bisector. So by just definition of angle bisectors, okay? Now, I'm going to mark that. We know that this angle is congruent to this angle. That's what those little arches mean. Don't forget that. We can also prove that the center line, which is a part of both of the triangles, is congruent to itself. We could say that line OP is congruent to line OP. And that is the reflexive property of congruence. So we know that the center line, I know this might be kind of weird, but I'm going to draw two hash marks on it saying it's congruent to itself. That's kind of weird because there's not two lines with two hash marks, but it's congruent to itself. So we know that we have a side, an angle, and a side congruent to a side, an angle, and a side. So we can say that triangle MOP is congruent to triangle NOP by the side angle side congruence postulate. Okay. I hope that makes sense. It should. As we keep going, figuring out how to prove triangles are congruent, you're going to become a pro at this. I guarantee it. Let's go ahead and keep going. In the diagram, R is the center of the circle. If angle SRT is congruent to angle URT, which is already labeled in our diagram, what can you conclude about triangle SRT and URT? So what can you conclude about this triangle and this triangle? Well, they tell us that R is the center. So from the edge to the center of a circle, what do we have there? We have the radius, okay? And the radius of a circle, no matter where you draw from, is going to be the same. This radius is the same as this radius, which is the same as this radius. So we can actually say that all three of these lines are congruent. So here we have a side congruent to a side, an angle congruent to an angle, and this center line is also congruent to the other two sides, but the center line is shared by both triangles, so it's actually congruent to itself. So we can prove that these two triangles are congruent by side, angle, side. Side, angle, side. Okay, so we can conclude that the triangles are congruent by SAS congruence postulate. Once again, pretty simple, I think. I hope it's making sense. Go ahead and shout out to me if it's not, or if you have a different way of explaining it. But let's keep going. Okay. In general, if you know the length of two sides and the measure of an angle that is not included between them, you cannot create two different triangles. You can create two different triangles. Therefore, SSA is not a valid method for proving that triangles are congruent, although there's a special case for right triangles. Okay, so I'm sure everybody asked their teacher, well, when are we going to learn the SSA postulate? Even though I know you guys, you like to spell it the other direction, and there are no swear words in geometry, so that does not work. But in right triangles, there's a special case, and we won't call it SSA. In a right triangle, the sides adjacent to the right angle are called its legs. The sides opposite of the right angle is called the hypotenuse of the right triangle. So you have two legs and a hypotenuse. The hypotenuse is always the longest side. So here we go, theorem 4.5, the hypotenuse-leg congruence theorem. If the hypotenuse and a leg of a right triangle are congruent to the hypotenuse and a leg of the second right triangle, then the two triangles are congruent. So all you have to know is a hypotenuse and the leg if it's a right triangle. So first you have to prove that they're a right triangle to even be able to use a hypotenuse-leg congruence theorem. Okay? So example 3, we're given YW is perpendicular to XZ and XY is congruent to YZ. So I'm going to go ahead and label some things we know. YW is congruent to, well, we really don't know that. We got to prove that still, so I'm not going to label that. But we know that XY is congruent to YZ, okay? So first thing we're going to do, let's go ahead and just write our givens, okay? Now, I want to label that they form a right angle, but first we have to state that since they're perpendicular, they form right angles. So let's go ahead and say that angle XWY and angle ZWY are right angles. So we say that. And the reason we know that is because perpendicular lines form four right angles. We learned that earlier on in the book that when two lines intersect and are perpendicular, they form four right angles. Well, we only really care about two of those right angles, but I'm going to go ahead and label them. So we have two right angles there. Now, since they form right angles, we're able to say that the two triangles, triangle XYW and triangle ZYW, are right triangles. And that is just simply definition of right triangles. Okay, since we know they're right triangles, we know that we only have to prove that a leg and the hypotenuse are congruent. Here, we already know that the hypotenuses are congruent, so we only have to prove a leg. Well, I don't think we can prove that XW and ZW are congruent, but they share a common leg, which is WY or YW. And we can say that YW is congruent to YW by the reflexive property of congruence. I love that property because we use it all the time. Now we know that the center line that they share and the hypotenuse are congruent. So we can actually say that triangle XYW is congruent to triangle ZYW by the by the HL congruence theorem, hypotenuse-leg congruence theorem. Sorry. One more example and then we're going home, people. Or for me, I'm going to Dean's meeting, but no big deal. Example 4. If you know that line AB is congruent to CB, so line AB is congruent to CB, and angle ABD is congruent to angle CBD, what postulate or theorem can you use to conclude that triangle ABD is congruent to CBD? Or sorry, what postulate or theorem can you use to conclude that triangle ABD and triangle CBD are congruent? So this is definitely one of those questions that they're trying to trick you up on. Because if you look at these two triangles, it sure looks like they form a right angle. So a lot of us are like, oh, that's a right triangle, let's use the hypotenuse-leg. But we don't actually know that this intersects to form a right angle. But what we do know is we have a side, an angle, and both the triangles share a common side, so that's also going to be congruent to itself. So side, angle, and side. Side, angle, and side. So we can conclude that they are congruent by the SAS congruence postulate. That's all there is to it, folks. Not a bad lesson. Hope everybody's doing great. I love teaching you these lessons, so go ahead and feel free to like and subscribe to my channel. Comment whenever you want, comment questions. I'll do my best to answer them. Somebody just posted a riddle not that long ago. I loved it, and I didn't cheat, okay? Q was the only letter that is not in a state. Anyways, shout out to you, Gabriella. Everybody else, have a good day, and see ya!